Kreutzame. Thanks, coming back from lunch. This talk's about runtime security, and I'm really, really happy and want to thank the organizers for inviting me to give this talk here. I've been working on this is research, for quite a while, and this is literally the premiere where I present the first working runtime node local detection and how we can reconstruct attack trees on the node where the stuff is running within 1 minute. Yeah, let's get started with the team. I represent a collaboration with 2 CNCF projects where I'm blessed to be working with their lead maintainers. One is Dom Delnano, he works from San Francisco, and the other one is Matthias Berci. He's actually not too far from here in France, and without those two, my work would not be possible. My name is Constance, I'm a researcher, an independent researcher, and the work that I'm showing you is funded by 2 organizations, the FFG, the Austrian Research Founding Foundation, and NetID. And without much further ado, today I will not be talking about all possible attacks. I'm going to show you 3 increasingly complex attacks and how we can find them at runtime. We have shown in the past other types of attacks, and we have talked a lot about the SBOB, which you're going to meet in a second, and I'm just referring to the other talks today because we're doing something new. Now, let's talk about the problem of runtime security. It is, in a sense, that either I see nothing or I see everything. In a sense, like I have either way too many alerts or I have no alerts, and the runtime rules drift, right? And so when I classically want to do security forensics, I need to know today what attackers are going to be doing or I'm going to be looking for in 6 months' time, and to define what data I want to save so that I have it at a future point in time. And the problem is as old as time, is that if you save every single HTTP request, especially also the post request content, then you will very, very quickly have a petabyte type of problem. And anybody who's run a data center ever knows how difficult it is to deal with large data volumes. So the idea today is to put the problem to the node, basically saying how much of a single alert can I determine, can I pre-classify, and can I pre-correlate all the relevant data that an analyst might later need in order to make decisions while I'm still there, while I still have that incident potentially ongoing. So, and what do I mean with too many? So this is 10 minutes of noise, various runtime rules classified here. We're going to come back to this in the very end. Just so, like, if you as an analyst had to deal with 2,500,000 unexpected file access, well, it's impossible to deal with this. And the idea is today I'm going to show you the approach where we're going to have exactly that amount of noise, and the algorithm needs to auto triage within a reasonable time which ones of these alerts are actual incidents, even attributed ideally to a CVE or to an attack, and discard all of the other noise as noise. Right. I've actually already, the other thing, I'm actually also not just a CNCF ambassador, I also, as of today, am a NeoNephos ambassador, and that is a foundation that deals with sovereignty. And another thing why you might not want to ship your data to someone else is because whoever has these telemetry, this observability data, can reconstruct not just the attacks, but they can reconstruct what you're running, what you're doing there. And in the terms of sovereignty, it's also very interesting in how could I host all of my decision-making really inside my cluster, inside my own data center. So all that you see is work that we do for the military, and they are obviously interested in completely air-gapped solutions. Right. And one other big problem that we have in security in general is that there are things that we cannot see, that we know that we cannot see. And I also want to talk about a very famous attack today, where I'm going to talk about, okay, which parts do we know we can't see, and which parts do we then have to use as sort of bright lights. So, but before we get started with the attacks and how do we find them, which eBPF tools are we composing into a whole? And I don't know who came up with the Musketeer motto like 3 years ago, but it sort of stuck. And we have 4 players here today with us. We have Kubescape, a CNCF incubating project that wraps Inspector Gadget in its Kubescape node agent. That basically is a scanner over all the events. You could replace this with another eBPF similar tool. I work with them because honestly, they're just fantastic people, and it happened. And the other tool I think is quite unique. It's Pixie. Pixie is originally a runtime debugger, so a live debugger that discovers everything. So it has all of your protocol data, typically by default 24 hours in memory. The other thing that we have is the filter, and that is a so-called bill of behavior. So if you heard about SBOMs, this is what we postulate as a SBOB, which is maybe at some point a standard on how we can create runtime rules, runtime filters. And the last piece that we do is the data saver, the thing that actually makes the decision of what gets saved and what does not get saved. And our things that we're going to attack is log4shell, argo path traversal, and react to shell. And don't worry if you don't know these particular attacks. I'll go through them. So, and now in a architecture-like diagram, what we see here is what you need in order to run this is at least one node of one Kubernetes cluster, and you need 4 daemon sets to be running on that cluster. One is Kubescape node agent. So what does it do? Its function is to have a coarse filter at any point in time. So this is the thing where I will describe any application that I'm running on with what do I 100% understand about this application's properties. What does it mount? What capabilities does it have? What executables does it have with which parameters? And the difference between a SBOB and any other runtime rules that I know of is that this is as coarse as possible. And we're going to come why that's important in a second. So one thing, at any point in time, we have a coarse grained filter. And the other thing that we have is for all time spans, we have a time series of all protocols, anything that goes over socket, and that's what we do with the Pixie Edge module. And the other 2 things that we need is the decision-making algorithm and the write algorithm that basically exports the data out of band to a forensic database. So let's do it by example. And we're going to start with log4shell. And we're not going to put any noise for now. We're just going to understand what are we actually looking for, keeping in mind that normally we have thousands or millions of false alerts. And the way we're going to capture is, by default, we capture nothing. The approach is we have the coarse filters, and if they catch some bright spot, then we're going to look backwards in time, immediately start creating a forensic shard with a hash, and then we're going to auto-triage, so these are out of band, whether or not what's happening in this time window is malicious or not. And then we can either delete what we've written or decide this is actually something we need to save. And this is now upstreamed actually in Pixie has now these queries that you can define at runtime, so in a graphical way. But and this is already available now. What I'm showing you now is the stuff that is not yet available, that is work in progress, is the dynamic adaptive decision making that we're doing. All right, so log4shell, Andy mentioned it this morning. It was one of these heart attack type of things. So we had a Java logging library that was vulnerable to string injection. What would happen is, so what we've got deployed is an Nginx, we have a Java service, we have a Postgres, and we have core DNS or some DNS server. And the attack is going to come in via the string injection. In Nginx, we're not going to see anything. So even though the string comes in, we're not going to check by default every HTTP traffic. Then in the backend, what happens is it reaches out to a typically an LDAP server from which it downloads a payload, and then it executes this payload into a shell, drops into a shell, and from there onwards, it can do, well, whatever, it's remote code execution, it can do whatever it does in the shell. And in this particular case, we're letting it exfiltrate data from a Postgres database via DNS in a base64 encoded string. Sorry. Yeah, so what we're doing here is simply on one node, and we want to know if just in this one node, we can identify this very, very well-known attack. So we're putting those 5 pods onto node number 1, and we have our daemon sets running. What do we see? So, and in this case, we have a very, very bright signal, and this is a super clear-cut exploit that we here have the complete attack chain visible in this middle process tree. So this is the wonderful power of eBPF. We see that we have an unexpected process that's a shell, and that's interesting. So this is it's a Java vulnerability, right? But the thing that we're detecting is not the Java part. The thing that we're detecting is actually that there's a shell. It's a binary that was not supposed to be launched by the JDK. And from that, since we can reconstruct all the children of the process, we can actually here see this entire one-shot attack. If it's contrived or not is not really the question here. What we also have at this moment, because this is the timestamp we now have of this process, and now we can look back into what we didn't see as an anomaly, what that the filter did not pick up is, hey, actually in the HTTP events, we saw that in the injection string, and also we saw that egress traffic to the LDAP, and we can resolve that thing in plain text. And why is this important is when we look at the attack not working. So in this case, I'm using the exact same setup, but I'm using a distroless image. So there is no shell in the distroless image. And obviously, I'm doing the same injection. The HTTP traffic is going to be the same. The Java download from the LDAP server is still going to be there, but we then have no shell. This process never gets spawned. And this is very important to understand. For example, you see a lot of traffic that looks suspicious, right? And you need to know, was I actually attacked? And it's extremely hard to prove when something did not work. And this is why we actually need to correlate all the traffic and all the actual payloads to see, did it work or did it not work? And then the other one that is invisible to this approach is when we actually patch it, right? And here in the WAFs, you would see a lot of these injection strings in the HTTP data, but you would not see any anomalies because neither shells are spawned, nor because the exploit itself doesn't work. So that Java lookup to the LDAP server is never actually happening. Okay, this is all cool. And now you're like, yeah, this is also very obvious. Constance, this is a super famous vulnerability, and we all saw it in that one process tree. Now, but what if you wanted to do this for all possible applications in all possible languages? And how would you train such a coarse filter, such an SBOP? And what you see here is how I let the AIs train, in this case for a Postgres, such a coarse-grained filter. I'm basically defining across the MITRE attack chain different stages, and I have a vulnerable version and a non-vulnerable version, and I'm checking which types of exploits work and if I can see them. So I'm constantly running this entire detection chain, and I'm classifying what entries do need to be in that YAML, in that signed YAML, what we call an SBOP, so that it's as coarse as possible while still seeing the actual vulnerabilities in that bright, clear detection, so that in a single JSON log, I get that what we earlier saw, this very dense piece of information. Now, this was cool. It worked. So we saw a very well-known vulnerability attack exploited. Now, let's add a second attack on the other node. And in this case, we're taking a path traversal vulnerability from Argo CD. What happens here is essentially, if you render Helm or customize, during the render, you can path traverse down into sensitive files, for example, and steal tokens and secrets. And that's exactly what happens here. I will not go into particular details. So again, we still have our log4shell running, and we also have this Argo guy running. We're rendering this malicious payload within Customize, and then we see we have a sensitive file access. Also, what we see now is the protocol resolution. Basically, Argo is not just one pod, right? Argo consists of many pods, and there's like something that does the Git and something that serves the repos, etc. And we can now reconstruct how the hops happen between these points. And that's going to be interesting in the next step when we're wanting to reconstruct now node locally that then tag spans across two nodes. How do I do that? What we do in this case is we're letting Argo deploy a React application, so a node application with the React to shell exploit in it, so that enables an attacker to steal, in this case, a token from the React application. And so Argo deploys a vulnerable application, and somebody then uses the stolen token in order to exploit Argo again. So it might be contrived, but the idea here is, so I need to do each of the identifications locally, and I need to cross-correlate it across the nodes. And the way I do this is now I create a cache of all pods that ever talk to each other, and so that I have a map of the network. And the moment that I have one of these violations, I then cross-correlate over the past 24 hours which connections have been made, and do any of them have open edges, right? And especially where any of these suspicious, like high entropy kind of connections, and how do the timestamps correlate? And also, of course, I have all the usual rules that I always have, like what's the sensitive file access, etc. I have all of this going on as per usual. But the cool thing is now, again, so I have this one big violation of the rule here. So for React, we have the service account token was read. That is a very loud kind of noise. And we also have, there was an unexpected call to the API, to the Kubernetes API. That wasn't in that filter. And on the Argo side, I have, again, this malicious render of the customized manifold. And now, so these are literally the anchor points that I'm taking in order to start correlating the entire network graph and filtering out all of the things that were suspicious or fit into any attack class that we know in the in the Microsoft Kubernetes attack model. And this was, again, we only had known things, and we just basically said, okay, the algorithm can see something that when we know what we're actually looking for. But the real problem is, how do we get the data volume down? How do we get the alerts? How do we get rid of the alerts? And that means that I need to discard all the stuff that wasn't relevant, right? And this is why I put a way to make all of the alerts super noisy in the following way. So I had these attack pods, right? But there's also a lot of other pods that are always running. The monitoring services, the database services, Pixie itself, ClickHouse, as here shown, but also Prometheus and CoreDNS and whatnot. And what I'm showing here is actually how this YAML, how such an SBOB is constructed, typically a couple hundred lines of these objects filled out. So anything that is filled out is an allow listed glob, typically a wildcard of something. And here I'm allow listing absolutely nothing. So I'm putting on all of my pods, apart from my vulnerable pods that we showed earlier, I'm putting a allow list nothing on it. And that means I'm getting every little health probe that does bling is going to bling up. And this is how I'm creating this excessive noise. And the algorithm needs to triage every single of these alerts that are generated from all the stuff that we know is actually, we know that it's nothing, but I'm testing the algorithm now, like, can it discard all of that nonsense in real time? So, same thing again, we're still doing our contrived or not example where, you know, Argo spawns React and React then exploits Argo, and we still have our log4 Log4j going, and we're firing these attacks once in a given time window, and at the same time we're flooding the system with K6S, which is a noise generator for functional traffic of these apps, and we're creating all of the false alerts. And yeah, so again, this was the thing I showed in the beginning. So during this time window where I'm running each attack once, I'm also getting all of this stuff, and yeah, I think 7 of them are real. The rest is garbage, right? And the question really is how can I identify? Can I still identify the attacks while I have all this crap going on? And now I'm having the same slide again. I don't know why. So anyway, so this is how I actually run this now. If I do these experiments, I have 2 AI agents. Typically more, but in this, let's say 2. One runs the experiment and the other one creates the attack. And they are not allowed to talk to each other. And they need to put it in an encoded envelope. So the agent that creates the attack puts it in an encoded envelope, and the other agent is instructed to not decode it. So it's not allowed to know what it's testing for. So by the way, this is all completely deterministic. There's the AI agents just execute all of this testing because there's a lot of testing going on. So we've got all our daemon sets running and so on. And so here, fire the sealed attack. Somewhere the second step here is it applies the manifest. It doesn't know, the agent doesn't know what it's looking for, and the other one needs to check all the daemon sets for the actual triage. Is the triage and the verdicts, are they coming in? And we see that we still have the malicious service account token read. We see the Kubernetes API connection. We see the big alerts. And we can also identify, there's something cross-pod. This in the very down here. Something, there were edges that were dangling. And we can reconstruct that the 5 pods in Argo were actually talking to each other. We had one thing that didn't work out. So the one thing that we couldn't correctly classify was the Argo malicious render. And here our algorithm, unfortunately, at the moment still gets starved out. That means it cannot query fast enough to resolve all of the potential investigations. And just to see you, the query went to 150 seconds, which is not great. And it was trying to resolve almost 5K investigations at the same time. And so it was reporting a false negative here. But it did find the other 2 attacks that we showed again. And the really actually important one is the last line, is all this benign crap was classified as benign. And that's just amazing. At least I found it pretty amazing that we could, we had, I think it's like 7 or 8 of these reports of these 2,000, 2,500,000, whatever, rule violations were there, and 7 of them were real, and we could identify that in real time. So the real game here is, of course, I said it's very, very hard to manage these data volumes. And the question I'm supposed to deliver as part of this project is like, how much data volume do we save? And you see here that don't cite this. This is anecdotal, because this is very, very hard to judge, like, saving as compared to what, right? The first thing is we need to rule that which is benign to be the benign, and we need to rule what is malicious to be malicious. But then here I'm showing that on my little K3Ss on which I usually test, I just checked like basically what is read by the adaptive service versus everything in that time window that went over, in this case, the HTTP and DNS protocols. And so you see that there is a big ratio, that it subsamples. But I mean, the reason why I don't want to give ratios is because the size of your cluster, how many of those pods are being attacked versus not, there's no normalization that I have figured out at the moment. The big finding for me was that we constructed well-known attack classes. We let one AI agent write the exploits, the other one and seal it. The other one had to steer the detection, which again, there's no AI in the detection itself. It just needs to do the experiments. And they don't know anything about each other. We can put load on it, and we can sometimes, mostly, identify that the benign stuff was benign. And that's really the cool thing. And I'm coming to the end. Thank you very much. The big takeaway was this idea. We want to have in real time a combination of two techniques. Sorry, we want to have node locally real-time triage, and for that we need two techniques. One was we need to identify a good coarse-grained filter, and why it's coarse is also because it's low. That makes it low maintenance, right? Because a big problem of runtime security is also that the rules, you calibrate them if they're very fine-grained, and 5 minutes later people deploy different stuff, deploy different workloads. They are out of date, and the other part that we needed is the ability to, once we have such an identification, is to look backwards in time and to reconstruct what happened before you had that one big anomaly. And that made it possible to cross-correlate across the different identification parameters in the kernel what actually was benign. And yeah, information density, that is the big goal, is like how can we save data volume that people do not actually have to store it elsewhere. This is ongoing, but it's going to be crucial for anyone trying to get the cost down that it takes for a human to actually understand what was going on. And what we get, even if we don't have the data volume itself reduced, what we can reduce here is the time it takes to correlate stuff, because the algorithm does give you the pre-correlated data. Anything that we can see in the kernel, we are pulling it together and throwing it into one hash, pre-correlated, that the analyst at least doesn't have to search. And also timestamp wise is pretty cool, since we're node local, we're all using the same kernel. So oftentimes you have problems with timestamps across different tools. And in this case, we don't, because we're literally on the same kernel. So the timestamp should be the same one, exactly the same. And we can actually nail down what happened in, okay, eBPF has a certain latency period, but apart from that, we can actually nail down the timing. And what we did in order to achieve this, we took two CNCF projects that exist. We did not modify them by itself, but we built two small little daemon sets, one that basically just either writes or doesn't write, and the other one that makes the decisions. And that was the one that we basically saw now that can identify, based on fundamental aspects of the kernel, can identify if a attack was, if an event was malicious or benign. And with that, if you wanted to contribute, or if you think this is cool, or I'm always looking for attack scenarios that I can build out, because I'm a blue teamer, I'm a detection engineer, not a red teamer. So I'm often inspired by people sending me DMs, or hey, this is a cool attack, here's a cool write-up, or so, and always interested in that kind of sort of info. And the other thing is we have a cloud native community group called Security Native Europe, and we're planning to come to Zurich in Q4. So maybe I'll see you there. We're also looking for speakers. And with that, I think I'm even in time, and want to thank again everyone who's on the foundation side who's supporting me here to do this research independently. And I thank you for your time and for listening, and the organizers for inviting me to be here. Thank you.